Good morning, everyone, and a warm welcome to the Nobel Laureate Lecture by the Bhaktivedanta Institute, Kolkata. I'm your host, Dr. Aristotle, and before we start, I'd like to invite Roshan Tiwari, Dr. Roshan Tiwari, to lead the invocation.
ॐ ईश्वर परम कृष्ण सच्चिदानंद विग्रह अनादिरादिर गोविंद सर्व कारण कारणम चिंतामणि प्रकर सद्म सुकल्प वृक्ष लक्षावृते सुशुरवीर विपालयन्तम् लक्ष्मी सहस्त्र शत संभ्रम सेव्यमानम् गोविन्दमादिपुरुषं तमहं भजामि वेणुवनन्तमरविन्ददलायताक्षम् बर्हावतं समसिताम्बुदसुन्दराङ्गम् गन्धर्वकोटिकमनीयविशेषशोभम् गोविन्दमादिपुरुषं तमहं भजामि आलोलचन्द्रकलशदवान्यमाल्यवंशी रत्नाङ्गदं प्रणयकेलिकलाविलासम् श्यामं त्रिभङ्गललितनियताप्रकाशम् गोविन्दमादिपुरुषं तमहं भजामि गोविन्दमादिपुरुषं तमहं भजामि गोविन्दमादिपुरुषं तमहं भजामि.
Thank you very much, Dr. Roshan Tiwari and team. So once again, it gives me great pleasure to welcome all of you to today's Nobel Laureate Lecture, which will be delivered by the esteemed Professor David J. Wineland. And his topic is titled My Journey of Discovery. This lecture is organized by the Bhaktivedanta Institute, Kolkata, and this is in conjunction with the BI's Golden Jubilee celebration, 50 years of Bhaktivedanta Institute. It's also organized in association with the Bhaktivedanta Institute, Alagada, Bangalore, Bhubaneswar, Hyderabad, NCR Delhi, and Vijayawada. I'd like to also acknowledge our knowledge partners, IIT Hyderabad, the School of Humanities, Social Sciences and Management of IIT Bhubaneswar, IIT Tirupati, Dr. T.D. Singh Quest Club from IISC Bangalore, as well as Jignasa Science, Consciousness and Inner Quest Group of IIT Bhubaneswar. Other knowledge partners include SOA University Bhubaneswar, Amity University Gurugram, Sanskriti University of Mathura, Sister Nivedita University of Kolkata, as well as the Government PG College of Ranikhet. And special thanks goes out to all our esteemed educational institutions who have helped to make this event a grand success. These are the different institutes that have helped us in organizing this event. Now it gives me great pleasure to invite the Director of the Bhaktivedanta Institute, Kolkata, Sri Varun Agarwal, to deliver his welcome address for this event. Sri Varun Agarwal, sir.
Namaskar. Hello, everybody. Welcome, David, and good morning to everybody joining from different parts of India, and good evening to those who are joining from the United States. My dear participants, professors, faculties, professionals, research scholars, Bhakti Institute members and volunteers, and my dear students. On behalf of the Bhakti Institute and its entire dedicated team, on behalf of founder director Dr. T.D. Singh, and on behalf of my esteemed colleague, elder brother, and president of this organization, Vasudev Rao, we heartily welcome all of you for this special lecture by Professor David Wineland from the University of Oregon, USA. Let me express a few words about this topic. Today, our topic is Journey of Discovery, as many of you must have seen. Let me express a few words about discovery. Our founder director, Dr. T.D. Singh, often used to discuss about creativity or discovery and what is this process. While meeting renowned scholars, scientists like Charles Towns, Roger Penrose, William Phillips, he used to discuss often how did you get really the idea, how the new idea came to you. So, what the process you underwent. So, this lecture is inspired by his vision and his interest in the discovery and its process. The journey of discovery, as many of us know who undergo this is full of excitement and mystery. It brings to life the dramatic and enthralling character which research involves. Means why? Because the researcher gets propelled by newer knowledge and getting close, a step closer to truth. So every step you make closer to truth, you feel energized or inspired. So, on one hand, there are two parts to this discovery research, this journey of discovery. One is the hard work, the persistence, the commitment, and the patience to walk in this journey. But then beside this, there is another aspect which is the inner experiences and the flashes of insights which the person, the researcher undergoes. So, this current lecture by Wineland, the idea is that this journey to bring out the complete picture, the complete journey or the whole story of researcher, the contributions, the technical scientific contributions, as well as the personal inner experiences which he went. And these personal inner experiences involve feelings of astonishment, joy, contentment, clarity, certainty. When you get something, you are very clear that certain this is it. And then humility, and then strong conviction that this is correct. And then sometimes even heart-touching gratitude to the Almighty for the gift of newer knowledge. And regarding the flashes of insights, there's a lot of discussion by many scholars, scientists from different fields, and different people get in different ways. Some get like a stroke of lightning, and whole path becomes clear in a moment. For example, like a mathematician, he was talking about how, suppose you are climbing a mountain in the dark, and then suddenly in the out of sky a lightning comes and the whole path becomes clear. Where are you? How to go? And then in a moment, and then you are clear how to go out. Or for others, it unfolds gradually. So there are like Francis Jacob, who got Nobel Prize in Physiology, used to describe it very nicely, this journey of discovery, in two parts. One is day science, another is night science. Day science means the logical side, the deductive side, which we are generally known to us. And the night science means the aspects of inspiration, the intuition, the inner feelings which the discoverer undergoes. And same Henry Poincaré, the famous renowned mathematician and physicist Pauli, they used to describe this in detail along these lines. So let me express a few words about the organizer of this prestigious event, Bhaktivedanta Institute. Bhakti Institute was founded in 1974. As Aristotle mentioned, this year is 50 years. The logo of the institute mentions a verse from our ancient Indian Vedanta, which is titled as first verse, Athato Brahma Jigyasa. Sanskrit words, Athato Brahma Jigyasa. And Jigyasa means inquiry. So the whole verse means inquiry into the absolute. So institute promotes inquiry or curiosity into the meaning and purpose of life, of universe we live in, and focus is on the foundational questions like what is life, what is consciousness, why are we here. So it believes that in search for answer to these questions, a multidisciplinary approach is necessary. Like Dr. T.D. Singh used to say, that in this answers to these questions, you need scientific aspect, modern technical know-how, as well as ancient traditional wisdom. So this combination of various disciplines will really help to get answer to these foundational questions. So this year we are celebrating 50 years. So let me share with you a few things which we have been doing. When a few slides, little bit. Okay, here it is. So we started the journey with a Phillips lecture, William Phillips, who also got in physics from Maryland. And David knows him very well. Um, he worked in laser cooling of atoms. In this January, we had this lecture. And then we had this program of Origin of Information, summer school, 3-day very brainstorming. Many scholars from different parts of India and from outside they joined. And then we had this focused conference on science of consciousness. Many scholars from India, abroad, they took part. This was in Calcutta, Yadavpur University, and just 2 months ago. And then we just had a conference in Bangalore in ISC in machine, mind, and consciousness. Just 2 weeks ago, we came from there. And we released a magazine, the Tattva Jigyasa magazine this year. Very interesting articles by this one beautiful article on Pascal about his full life, from his scientific contributions in mathematics, probability, and to his inner experiences and life. And then there's a good article on computer, brain, and consciousness, and then dialogue with Dyson, the famous physicist, and an article by MIT physicist, IQ of our universe. And this is upcoming. AISSQ, the conference, the annual conference started by the founder, Science and Spiritual Quest, in end of this year, 28-29 December. And it will feature also a lecture, special lecture by cosmologist Ganzel, Professor Ganzel from Germany. He worked on the black holes. So these are some of the things which we have been doing. Well, so let us today welcome David Wineland, and we are very delighted to have him. His amazing discovery of trying to experimentally capture ions with the help of photons, this revolutionized our physics and our world, which has theoretical implications to practical applications of upcoming, very soon, I think, quantum computers and optical clocks. So we once again welcome all of you to this exciting journey, inspiring and enlightening journey of discovery by world-renowned scientist Prophet David Wineland. We hope his words of wisdom, knowledge, and personal experiences will fill all of us with tremendous insights and inspiration in our life and in our works. Thank you. Thank you very much.
Thank you so much, Sri Varun Agarwal, for that insightful and wonderful welcome address. Before we begin the lecture, I'd just like to remind the audience, please scan the QR code to ask questions to Professor David Wineland. You can ask your questions. You can submit your questions during his lecture so that the questions bank can build up, and the moderator will be able to present those questions to Professor Wineland. I would like now to invite Professor Prabhat Kumar Singh to introduce our esteemed speaker. Professor Prabhat Kumar Singh is a professor at IIT BHU Varanasi. Professor Singh, please.
Good morning to all. Welcome, Professor David. This is my proud privilege to welcome you and introduce you. In my young days, I started learning physics. So my life started with physics, and I'm a crazy person around physics. Today, I'm a civil engineering professor, but still I work with a lot of physics. So it's an honor to me to introduce you. David J. Wineland is an American physicist celebrated for his groundbreaking research in quantum mechanics and atomic physics. He has shared the 2012 Nobel Prize in Physics with Serge Horsch for developing methods to observe and control individual quantum systems, particularly trapped ions. Wineland is currently a professor of physics at the University of Oregon. Wineland received his PhD in 1970 from Harvard University, where he studied under Norman Foster Ramsey Jr. Following his PhD, he conducted postdoctoral research at the University of Washington, working with Hans Deckmelt. Wineland joined the National Bureau of Standards, later NIST, in 1975, where he conducted pioneering research for over 4 decades. His research focuses on quantum state manipulation of atomic systems with applications in quantum information and quantum limited meteorology. In 1978, Wineland and his team developed laser cooling techniques, achieving the first successful cooling of ions. This technique, known as Doppler cooling, allowed precise control of ions at quantum levels. His research demonstrated that single atoms or photons could reveal unique quantum behaviors and be used in practical applications. In 1995, Wineland and his team achieved a significant breakthrough by placing ions in quantum superposition. That same year, his team conducted one of the first quantum logic operations with trapped ions, establishing ion traps as a promising platform for quantum computing. His research also led to the development of an advanced atomic clock using quantum logic on a single aluminum ion, achieving unprecedented accuracy in timekeeping. This set a new standard in precision, influencing the design of future optical clocks. Wineland has published more than 600 research papers in scientific journals, making a substantial impact on quantum science. His works have contributed significantly to the field of quantum information processing, quantum optics, and atomic physics. In addition to being awarded the Nobel Prize, Wineland has been recognized with numerous prestigious awards. These include the National Medal of Science, the Davison Garmer Prize, Arthur L. Shallow Prize, Benjamin Franklin Medal, and Messias Quantum Prize. He is a fellow of the American Physical Society, Optical Society of America, and a member of the National Academy of Sciences. With these words, I welcome you, Professor Wineland, and we are very eager to hear your inspiring words and the journey towards discovery. The floor is for you now, Professor David.
Okay. Well, thanks for the nice introduction, and thanks to all the students and senior people attending the meeting here. All right. Well, this is my story. It sounds a little pretentious, my journey of discovery, but maybe I've made a few discoveries, but mostly it's been fun with working with other people on these problems. And so anyway, I get a bit of background for me is that my parents experienced the Great Depression in the U.S. which lasted from 1930 to 1940. And so, that with that experience, there was certainly when my sister and I were growing up, there was an emphasis on us eventually getting a college education so we could find a good job, because during the Depression, many people just didn't have any jobs. And so, but my parents were lucky; they both had jobs during the Depression. So, but anyway, so they certainly educated or emphasized getting a college education when I was growing up. And what that meant is making good grades in school and So I was raised in Sacramento, California, and so that's where I went to high school and grammar school. So, but my parents, although they emphasized the importance of doing well in school, but they gave me a lot of freedom to explore. So I've always been interested in mechanical things, and it started out with model airplanes, for example, and later um, when I got older. In fact, I got my first car at age 14, and I couldn't drive it until I was 16, but my father brought it home, and it needed a lot of work. So, so I tore down the engine and fixed it up and so on. But I mean, that was a good experience for later because I learned a lot of mechanical things working on the car. And so this continued, the car thing continued with when I was in high school. And I mean, we would buy cars and fix them up and then resell them. And anyway, so we had a great time doing that. Whoops, sorry. Um, and anyway, but during my first physics class I took in high school at age 16, and what I liked, I was always pretty good at math, and what I liked is that relatively simple math could explain a lot of the things we find around us, and I think that's really what led me eventually into physics career. Actually, so when I started after high school, when I went to the university, I started first at the University of California in Davis. That's close to where I grew up, close to Sacramento. But Davis was primarily an agricultural school, and so I went there 2 years, and then because physics, the Berkeley was the place where all the strong physics programs were. So basically I transferred there, and there was no, since I was in the University of California system, I basically just had to submit a paper that I was going to show up. So that made it very easy to transfer to Berkeley. And then as was mentioned, after graduating from as an undergrad, I went to graduate school at Harvard University. And so this is when I went to Harvard, I didn't I actually thought I started as a math major in college, and then I basically, so I had a good mathematics background, but when I got to the university, I learned what experiments were like, and I was able to join up with Professor Norman Ramsey's group, and anyway, so that and so that's the younger me over there, and that Norman's on to our right in this picture. And this was the entire group last time, and so or that time, and so many of you may know Norman was famous in atomic physics and molecular beams and things like that, and he actually shared the Nobel Prize later. Anyway, so this was the group then, and my thesis was. Well, I should back up and say that Norman and his colleague Dan Kleppner had basically invented and then demonstrated the first hydrogen masers. And and just to back up a little bit, masers are basically the same as lasers. They work on exactly the same principles. And in fact, the first devices, demonstrating the laser or maser principle were actually masers. And so, laser, pardon me, laser, the M in maser is, replacing the L in laser for microwaves, and that is that M. And so that's why it's called a maser. But anyway, so Norman and his colleagues they had measured the hyperfine frequency of both hydrogen and tritium. Tritium, it turns out, it has almost the same wavelength and frequency as hydrogen, so it was easy. They could use the same apparatus. And the idea, I mean, as I say, the idea is very much the same as a laser. We find some way to put atoms in an excited state inside of a cavity where they radiate, and we pick out some of that radiation. And the only difference was that deuterium had quite a bit longer wavelength, and so one of the main things is that it had the size of the cavity for the maser was on the order of a meter in size. And so, but otherwise, there was a lot of similarities with hydrogen. And anyway, so my main task was to give a precise measurement of the deuterium hyperfine frequency. And that, for those who don't know, the hyperfine frequency is just the energy is determined by whether the outer electron is parallel or anti-parallel to the nuclear nuclear spin, and that the difference in those two configurations then gives rise to the transition, which in deuterium has this value of about 327 megahertz. Oh yeah, so anyway, so this is kind of embarrassing these days because there was actually in there, you can see there's no women in the group there, and in fact, when I went to grad school, the entering class in physics was 26, and there was just 2 women in the class. I think times have changed. I don't, there's a lot of sociological reasons why there weren't so many women at that time, but I think things have changed a lot now. And certainly women are equals with the men and certainly in physics. So that's changed a lot. Well, anyway, and it turned out Norman, during the time I was there, this was roughly 1965 to 1970. He was actually involved, heavily with the organization and build-up of Fermilab, one of the main particle accelerator facilities in the U.S. And so he actually wasn't around very much. He would come in almost every Friday, and we'd have our meeting. But otherwise, he was in near Chicago, where Fermilab was being established. But he still we had a good meeting every Friday. And but one nice thing was that because he was gone a lot, we basically just helped each other with it. That was critical, working in a group like that. And actually it was a lot of fun to work with the rest of the people in the group. So anyway, so then I went to as a postdoc, I went to work with Hans Stamos at the University of Washington. And so Hans had gotten his training. He was familiar with trapping both atoms and electrons. And the one experiment he was pushed on, and the one he's most famous for, is to measure the magnetic moment of the electron. So one of the properties of the electron is it has a magnetic dipole. And so the experiment, I won't go through all the details of how it was measured, but Hans made an experiment where he could measure this magnetic moment. And just to give you on the left part of the picture there's a schematic. This is the blue lines are meant to represent some electrodes, and it's sort of a cross section. These two horizontal lines there that just cuts through a cavity. So there's a ring shaped kind of cavity around and then along the axis there's a magnetic field, and then there's other potentials on the what we call the end caps. And anyway, in any case, this would form a stable trapping device with a magnetic field applied. And so that was the basic setup for measuring electrons. And I mean, one thing, it particularly for the motion along the axis here, you can think of, it's a harmonic. The trap is set up to basically mimic very well a harmonic potential, and so, but a simple picture of that is just for motion along the axis is like a marble rolling back and forth in a bowl. And anyway, but the turns out that this electron inside these electrodes would actually look like a harmonic pardon me, LC circuit, and where the inductance is represented by the inertia of the mass of the electron, and the capacitance is expressed just by the coupling to the electrodes, the electric coupling to the electrodes. And so anyway, we can think of this whole system here as an LC circuit. Then we can put that into a circuit, and we could drive at the resonance frequency. We could drive and see the induced the currents that were from the electrons inside the trap. So the goal experiment, Damelt had been out on this experiment already he had been trying to use an ensemble of electrons. And it turned out that when I got there that, after discussing things for a while, the problem was there was ways to detect there were many electrons in the trap, but there were perturbations that are very hard to control. But it turned out a lot of these problems would go away if we could experiment with just a single electron. And so that was one of the main things I was involved with, is to be able to reliably produce single electrons in the trap. So basically, we would load a lot of electrons, and for example, we could ionize some of the background gas to load up electrons, but we didn't have a way to individually load them. So we would load in we called it a cloud of electrons, but it would be on the order of 1,000 or more. But we wanted to get down to one, and so the way we were able to do that, because it turned out that the systematic effects would be much better, easily handled if we could put a single electron, work with a single electron. And so the way we did that is we put some number of electrons in the cavity, and then drive the potential across these two plates. And as I say, it represents this LC circuit then, and we drop the voltage that was passed through, and then amplify it. And so this is the kind of thing we'd see. So to get down to single electrons, we loaded a certain number, in this particular example, 7, and then we would just turn the source, the oscillator source, up to kind of a critical value where occasionally one of the electrons would either hit a background gas atom and be diverted out of the trap, or for example, there would also just be dissipation or some noise in the system. But anyway, what you see here is we drove the motion, this pseudo LC circuit with such that it was just at some critical value where we'd see loss of individual electrons given by these steps here. And then of course, when we could reproduce this. And so when we got down to the last step, then we had our single electron to play with. And anyway, I won't say much about the magnetic moment of that experiment. My part, I didn't actually play a role in the actual measurement of the magnetic moment. It was more getting to being able to isolate single electrons, and so that eventually the magnetic moment of the electron was measured. And now this is remarkable experiment, I think, because the uh, the the electromagnetic moment, it turns out, after the first experiments and then subsequent measurements to measure the magnetic moment based on the basic same idea I've described here, is that the precision improved. So now it turned out the measurement of the magnetic moment of the electron can be measured to within a certainty of about 1 part in 10 to the 12. And what's interesting is that the theory that predicts the magnetic moment can also reach that precision. And so I think this is, and that the theory is basically quantum electrodynamics. And so one of the wonderful things about this experiment is basically it's the most stringent test in terms of precision of quantum electrodynamics. Yeah. So anyway, Damalt and Norman Ramsey, they shared the same prize for different things, of course. They shared the Nobel Prize in '89. And so anyway, that was my training on trapping. And as I say, I wasn't in on the first measurement. The first measurements of the magnetic moment were done after I left there. And this is one of the first references for the magnetic moment measurement. So anyway, after my graduate work at Harvard, I moved there. There was a position that, and then after my work with Damalt, there was a position that opened up at NIST, and they wanted someone to. They had made a new cesium atomic clock, and they wanted someone to evaluate it, and so that was one of my first tasks to do that. But anyway, the cesium beam atomic standard was a stream, a beam of cesium atoms that would travel down an evacuated tube, and then when if the atoms were irradiated at the microwave frequency corresponding to the hyperfine frequency was around 10 gigahertz, then they would change atomic state and they could be deflected one way or other by inhomogeneous magnetic fields to detect the transition. So that's anyway. But to give you an idea, what the kind of things we worry about with atomic clocks is that, for example, and it's just sort of interesting to compare maybe with a pendulum clock or even a quartz crystal clock. And anyway, but I'll compare to the pendulum clock. And basically, we learn in some of our beginning classes that the frequency of the pendulum, if for small amplitudes, is given by the local acceleration of gravity and divided by the length of the pendulum. Well, anyway, you see the expression there. And so with atoms, of course, what replaces them this harmonic motion of the pendulum is the energy levels in an atom. And we do that because we can characterize the energy, the splittings, of energy much more precisely. And so just to compare, to give some idea of environmental sensitivity, that in the case of the pendulum clock, the rod that supports the pendulum, it's usually some material that expands or contracts with temperature, typically expanding. And actually, if we used even in a pendulum clock, we can find materials that are, with thermal expansion coefficients of about 10⁻⁸ per degree C. And just for comparison, most metals are about 500 times larger than this expansion coefficient. But anyway, you can find materials with very good, small coefficients of expansion. And anyway, the frequency uncertainty and then is given by this expression down here. And so it's almost a part in 10 to the 8 per degree C, the change in frequency. And so we want to get much higher precisions. So we have to figure out some way to do that. And one nice thing about atoms is, as far as we know, all atoms of a given kind are are exact. The frequency is exactly the same. So we have sort of a nature built-in standard of frequency. But then we do have to worry about environmental sensitivities. And I talked about the thermal effects for a pendulum clock. The one for atoms is much more interesting. It's due to the thing we end up measuring is we have to need to be able to characterize the temperature fairly well. And because of Einstein's time dilation effect, we have to do these calibrations. But it turns out, of course, the sensitivity is much smaller than the pendulum clock sensitivity. And so, for example, for cesium, if the temperature is representing the velocity of the atoms, then the fractional frequency shift is about almost 7 orders of magnitude smaller than it is for the pendulum clock. And this is certainly one of the reasons we head towards atoms. The other thing is, for say a pendulum clock and a quartz crystal clock, there's always some manufacturing intolerances. So the ultimate frequency depends on the manufacturing tolerances. And of course, with a pendulum clock, it depends on the local value of G. And of course, and also to some extent, there might be wear in the bearing that supports the pendulum, so that the rod would slowly lengthen to change the time. The nice thing about atoms and cesium atoms, for example, is that as far as we know, all atoms of a particular kind are exactly the same, and they don't wear out. If we can keep them around, they last forever under other than under harsh conditions that we don't have to worry about. So anyway, just to give some idea that in terms of time standards, I mentioned cesium beams already. That people had worked on them starting in the early 50s, and so that was the first time we used an atom to actually define the length of a second. So they measured the frequency as best they could by other means, including the rotation of the Earth, things like that. And anyway, but they defined the frequency of cesium to be exactly this number. And this is the definition of the second. That is that so many, if you count so many 9 billion and so many cycles, that defines the unit of time, the second. And I'll say a little bit more about this in a bit, but this is still actually the accepted standard around the world. And but I'll come back to that in a little bit. So, okay, sorry. What about ion? I'll get there in a minute. Sorry about this. So for atomic ions, for atomic ions, we make this electrode structure. This is similar to the shape we use for the penning traps too. The one we're using for atomic ions it's called the Paul trap, after Wolfgang Paul, who invented it. And it doesn't rely on the magnetic field like the penning trap does, but in this case, the trapping is in part provided by oscillating electric potentials on the electrode. So typically, those frequencies might be anywhere from 100 to a couple hundred megahertz, something like that. But anyway, by applying the potentials on these AC potentials on these electrodes, we can make basically a 3-dimensional harmonic well for the ion that be in the center of the trap. And again, we can actually in all 3 directions. In this case, the analog is like a marble in a bowl. So anyway, one of the things is I mentioned the problem with. I mentioned the problem with Doppler shifts for example, an atomic beam, and so one of the interesting things was, could we cool the ions down? And I actually had my experience was when I was working with Hans Stammel's lab. I was trying to learn about other things, and I was reading about at that time, the tunable lasers, for example, dye lasers, were just coming on the scene at that time. This really made revolutionized atomic physics. Could basically find a laser drive almost any transition in any atom. So anyway, but the idea actually in reading these papers about atomic physics and the strong forces that lasers could apply. I mean, I came up with this simple idea, and it's extremely. If you just give this ingredients to a student, anybody could figure it out. But the idea is that if an atom, just take a one-dimensional picture of an oscillating atom going back and forth. If the atom moves against if the laser beam, let's see if I put a laser beam. Oh, anyway, if the laser beam is coming horizontally in this picture, if it's tuned below the transition frequency of a particular optical transition, then when the atom moves against the laser beam, if we tune the laser beam to a somewhat lower frequency than its the atom's resonance frequency, when the atom's moving against the laser beam, the Doppler shift, if we tune things right, it'll tune the laser into resonance in its frame, so it can scatter a lot of photons. And of course, when it moves the other direction, it's tuned farther away. But when it moves against the laser and scatters photons, then its momentum gets reduced by the momentum of the photons that are scattered. And that's the basic idea of so-called Doppler cooling, where the cooling effect relies on the Doppler shift. And anyway, so there was a lot of when I went to NIST, I was lucky. I first worked on the cesium beams, getting things tuned up, but then I got one of my colleagues there who knew about lasers, Robert Drillinger, in this lower citation. We got some money from our laboratory chief, and so we could start an experiment on this. And anyway, so it's sort of an interesting near coincidence here. You notice Damelt had gone to work with Peter Toshak, and they were working on basically the same problem. And if you notice, our paper got published a little bit earlier than theirs does. But if I'm careful with this, their paper that was in a near coincidence almost. Their paper was received a day earlier at the journal than ours was. So you could call them the winners. But actually, in any atomic physics, in any of these experiments that require months or years to put together, I mean, if you do the same experiment within a month of each other, it's considered a tie, and I think rightfully so. So anyway, but that was an interesting near coincidence we had there. And anyway, this is the cooling that we saw, and you can see anyway, this is what we turned actually the laser power we had was really meager. You can see down in that abstract down here is about 8 microwatts. So it's pretty feeble laser, which was obtained by doubling a dye laser in a nonlinear crystal. But anyway, it was enough power, and there was very little parasitic heating of the ions in the trap. And so if we turn on the laser, we knew what frequency to turn on, and you can see the temperature fall down here, and then if we turn the laser off, then it'll gradually rethermalize to the ambient temperature, basically room temperature. And so anyway, so the effect was certainly there. It was not a strong effect, but we could see the effect of the laser cooling. And actually, one thing I wanted to say was what was nice is I mentioned when I got to NIST that I had one task was to measure or evaluate a cesium beam apparatus that they had. But the laboratory director, she was aware of this idea about laser cooling. And so my first colleague there, Robert Drollinger, who knew about lasers, Catherine Gebbe here, she was an astrophysicist, but by this time was more into management. But basically, she knew about this idea, and so basically, she gave us all the money we needed to get on this project. And so, one of the nice things that we started in an empty lab, and that is Bob Drollinger and I, and in about 5 months, we had the first results on the cooling. So anyway, this is a little bit later, and the group grew. This was Bob Drollinger, the guy who did the cooling with, and this is Jim Berquist, who was a laser expert as well, and this is Wayne Atana, who was our theoretical expert to keep us in line. Anyway, there's a lot of interesting things we did in these experiments. I've listed a few topics here. We could, just by measuring the size of the signals, we could isolate single electrons. One of the things that was popular then around that time was people just this idea of quantum jumps, and this goes way back to Schrodinger, where some people thought the atoms would instantaneously change from one level to the other, and there's a debate about that. But anyway, we could see these quotes quantum jumps in the atomic states. This middle topic was it was discovered with with X-rays, but the effect that was measured there is the phenomenon of the Mossbauer effect. It was just named after the person that saw it. But basically, for trapped, in his case, it was trapped nuclei. But whenever if there's an absorption event, that there's some recoil given to the nucleus, and in that case was nuclear, because it was nuclear transition. But the fact that with the nucleus was attached to the crystal it was in, basically all the momentum transfers goes into the rest of the apparatus, and so the effect basically goes away. That is, there's no Doppler effect, when single photons are absorbed. Anyway, that was, as I say, it was a big deal when I was in graduate school to see this Mossbauer effect, but we didn't see it. But anyway, so and not long after this, we could cool down the ion motion down to basically the quantum ground state with high probability. And anyway, that we developed one clock around Mercury, and that the laser part of that was headed up here by Jim Berquist, and it was an ultraviolet transition. But basically, we showed we could show that the systematic effects, that is the precision experiment, was better than could be done with cesium. And so certainly we started thinking a lot about atomic clocks based on ions. So I'm not going to be able to say a lot about quantum computation. This was another whole 1 or 2 lectures in itself, but I'll give you just some of the basic ideas, or at least some of, and that is that, so this idea of quantum computation was actually, it was started a little bit before we got into the game. But what's interesting is, as I say, I won't have time to go through all the operations, but basically, I'll give you the implementation. Peter Zoller and Ignatius Serac are two well-known theorists in atomic physics, and one of their strengths is that they pay close attention to what the experiments will do, and so they were knowledgeable about what the ion traps could do. And so basically, as I say, I won't have to go through all the details in here, but basically their scheme was, in this example, suppose we have 5 ions, and the 2 internal states will we tend to label them by arrows up or down, and this is just an analogy with the electron spin, which has two spin states in a magnetic field, and it's like any other two-level system. So, but this is kind of, we tend to talk about electron spins, but it's basically just two different levels. And the other thing is when we got down to these very low temperatures, we started seeing quantum effects in the motion. We could see the quantized motional steps. And so what's important in their proposal was that we'd have a qubit, a two-level system formed by some two states in our ion or in an atom. And then it also, if we considered both the ground and first excited state of motion, that would basically be another qubit. And so the idea of their scheme is that we'd isolate one mode of motion, and then with a laser beam we could actually transfer the superposition state of the ion into the superposition state of one of the motional modes. So just a mapping one-to-one of down the spin analog into these first two energy levels. In this case, we had to cool to the ground state to make this work. And anyway, the second part of the experiment, and again, some details I just don't have time to go through here, but is that if you could do a logic gate between the internal state of this second qubit that's focused on and the qubit that's forced generated by the ground and motional state of a mode which is shared by all the ions, and the simplest one to think about is the center of mass mode. But anyway, if we could make a logic gate between this motional qubit and the atom qubit, then basically by the mapping process we've made a logic gate between these two separated ions, and then we'd reverse the first mapping step back to go on to other operations. So this was the basic setup they laid out in their experiment. And they were nice enough to give us a copy of their paper on their idea for doing these logic operations. And anyway, we were in a very short time. They gave us a preprint of their paper, and we had been doing operations that were all the operations that were necessary. So just in a few months, we were able to basically establish what's called a controlled NOT gate, just one of any 2-bit gate that between the atom's motion and the atom's internal state. And that was sort of the key operation for to basically start to scale this system up with. Oops, sorry. So as I say, there's a lot to say here. First of all, there's now probably many of the students, other people in the audience know about the ideas of quantum computation, and there's the ideas, simple ideas I've laid out here, and for atomic ions, but there's superconducting qubits and photon qubits, that sort of thing. So there's a whole different technologies that are looking at this problem, and I would say there's no clear winner yet. There's certainly there's a lot of nice experiments going on. And actually, just one thing I can say is just in the case of ions, not everybody's working on trying to build a quantum computer, but there's about 100 different labs around the world that are actually doing the kind of operations that I've described here, trying to do more improved operations. But this is expanded a little bit, and so I mean, one of the things is, of course, I focused here on gates, and we can do simple algorithm implementations, and that's done by many groups around the world. And actually, after those first experiments, Didi Leibfried joined our group, and so we could do some simulations of other systems, and for example, the interacting ion dipoles that they can, we can simulate quantum magnets with those with these systems and so on. Anyway, so I list a few names that have been doing this. This is on the right here. This is a picture of a crystal of ions in a different trap. It's the pinning trap, the one that I first showed you. But anyway, you can see it low, and they're cooled. They're laser cooled, and you can see that makes a very regular array of ions. And so there's, the John Bollinger in our group at NIST, he was among the several groups around the world that were able to do characterize quantum many body problems using these lattices holding many ions, and and of course we can with the simple starting with the simple steps that I described to you for quantum logic, you can make some more general quantum simulators. And my close friend and colleague in Innsbruck, they've done a lot of experiments along those lines, as well as what John Bollinger did in our lab at NIST, and many others. And so one thing I will say is that I just want to give you an idea of where this can go. With some of these ideas of quantum logic, people are certainly thinking about quantum computers, but one of the nice things, because of our interest in clocks, one of the things that we started doing experiments on mercury transitions, but we found a better system in principle to make an optical clock, and that is with aluminum. And some of the nice features there is that it has these are two optical levels now, separated in energy with a wavelength corresponding to about 267 nanometers, and we could drive this transition. The question is, how do we detect it? And so in some experiments, there's a third level, and let's suppose we start the atom in the ground state, and then if we drive it with the clock frequency and are able to promote it to the upper level, then when we turn on this laser here, if the transition is not driven and the atom remains in the ground state, then we can see scattered light on this transition here. On the other hand, if it makes the transition to the upper clock level, then when we turn on this laser, we don't see any scattering. And this general principle is basically now used in all our experiments, and this essentially gives 100% detection efficiency of whether the ions make the transition. We demonstrated this with aluminum ions. Part of the reason is this in the aluminum is that this level exists, but the wavelength is so short that we didn't even try to find a transit, to make you exercise this logic on aluminum ions. We've done it with other ions. Anyway, but what we could do with aluminum is that it turned out what I'm representing here is the harmonic potential of the trap. And if we put our aluminum ion in the trap, the circle in blue, and we also put a magnesium ion, what we can do is that it turns out we can detect optical transitions in magnesium much easier, and so than we can with aluminum. So basically, the idea is, here's our aluminum clock qubit, and we can try to make this clock transition, and as I said, we don't have a laser that allows us to do this. But the thing is that if we try to drive the clock transition, what we could do is we can map the quantum state of the aluminum ion onto the quantum state of the the ground and first excited state of motion of one particular mode. And then so we just map the superposition of aluminum into in this example, into a superposition of two magnesium states. And the practical advantage is, after doing this the transfer, then we have a wavelength here with magnesium that we can, it's much more easier to generate. We call this a quantum logic clock, because we're detecting the transitions in aluminum are clocked by mapping to another ion and then measuring the changes of state with that atom. So anyway, the nice things about this too is when we're driving this transition, if we can do laser cooling on the magnesium, so it keeps the aluminum ion extremely cold, which is what we want to avoid the time dilation shifts. And also it turns out in magnesium there's transitions that are magnetic field sensitive, so we can, for example, calibrate the quadratic effects from magnetic fields or just the static magnetic fields themselves just by using the magnesium, which shares the same environment as the aluminum ion. So anyway, so we later went to this aluminum clock that I mentioned briefly, and these are the two Daves that had really set this experiment up. The aluminum ion wavelength was about 270 nanometers, and the upper state lifetime was about 20 seconds. And as we did the similar experiments in mercury, but the lifetime there was only about 1/10 of a second. So the lifetime here was 200 times longer than aluminum, than what could be done in mercury. And so this made for extremely high Q resonator. And we could basically, after several years working on all the systematic effects, we could get the systematic uncertainty down to a little under a part in 10 to the 18th. And the part in 10 to the 18th is sort of the gold standard right now. There's only a few labs that can reach that level of precision. And this, will certainly eventually get better. But this kind of gives you an idea where the imprecisions are, and they're down to part in 10 to the 18. Whereas with cesium, they're still at cesium atomic beams, for example, they're still at about a part in 10 to the 15 level of uncertainty. So this is really, in terms of accuracy, it's a big step forward with the aluminum. And anyway, I certainly want to say this was a group. I moved to Oregon a few years ago, but this was our group in 2018. And I described these experiments, but you can see there's a big cast of characters. We were doing a number of different experiments besides the clocks, but it was all the students here and the postdocs and visitors from other labs. At that time, there were just 5 senior staff like myself. So we relied a lot on a lot of visitors and help with the students and postdocs. And we also got NIST, we got some direct funding from NIST, but we got some also from other government agencies, that particularly ones interested in navigating, like the Office of Naval Research. Anyway, all I wanted to say was it just wasn't the couple of us working on these things to make them work. It was a huge number of people, and that's true of the other labs around the world too. And I also want to thank, I already mentioned Catherine Gebbe, who she was when we first had this idea about laser cooling, she was the one who immediately got us money. In fact, she was known for the fact that she would say her style of management was very simple. She said, find good people and give them money. And so she trusted us, and she trusted other groups too. But anyway, and that tradition was carried on by later, after Catherine retired, by Carl Williams, who was our lab at the time this picture was taken. So anyway, just say a little bit for actually some issues unrelated to physics, partly my wife's health. But anyway, we moved to Oregon to get back to sea level from Colorado, where we were before. And anyway, I won't go into all the details then, but we're doing actually I'm working with a former postdoc I had at NIST, and this is our group in Oregon, and we're trying to make quantum bits and frequency standards on, in this case, on calcium ions. And I won't go through all the details, but anyway, we're using calcium ions to do both spectroscopy, potentially clocks, and also to do quantum logic, quantum bits using these calcium 40 ions using different levels. Anyway, so that's going on right now, and of course I want to thank everybody for listening, and good luck to the students with your careers. So thank you.
Thank you, Professor Wineland, for your beautiful lecture. So I'm Dipankar Sharma, and I will ask some questions that we received from our participants on behalf of them. I'll present it to you. But before that, I would like to express my deep gratitude to you for this beautiful, inspiring, and insightful lecture. As a student of quantum computing myself, I was very happy to see these remarkable developments in this field of trapped ion, or neutral atom quantum computing, and yes, also the freedom that you had to explore during the childhood led to this beautiful journey of discovery of yours, which is truly inspiring. So I think it's fair to say that you trapped us all today, in the same way that you trapped atoms and ions in your research with very precision, elegance, and brilliance. Thank you so much.
You're welcome.
To start with, thank you. Maybe I would just continue in this line, and maybe I would like to ask one of the question from myself. So, as someone who has been in the forefront of such transformative research, what is your perspective on this practical application of quantum technologies that it has evolved over the course of your career in past few decades?
Well, I mean, certainly, we're still in the clocks are still a good business. But certainly, as you know, there's a lot of promise with quantum computing, and I think that there's a lot of nice work going on, but there's still a lot of difficult problems to solve too. That is to at least be able to solve large scale problems in quantum computing. So I think all the elements are there, but to put it all together on a larger system is, as you well know, it's just that's a hard technical problem. So I would say, the ions, they have their advantages and problems areas too. And at this stage, and superconducting qubits, of course, there's a lot of effort going in that direction, and there's other disciplines as well. But so at this point, I don't think there's a clear winner, and there's still serious problems that have to be solved. But I don't know, I think in the end it really will work and on a larger useful scale. But there's just a lot of technical issues that have to be solved. So
yes, certainly. I mean, I can understand we are in the University of Basel here in Switzerland. We are working with spin qubits and also superconducting qubits. And
yeah,
sure. Thank you so much for this. Okay, so next I take question from it's a combined question. I mean, it's a kind of similar question from many participants, like Jawahar Raja from Bharatiya University, so what are the implications of your experiment to the Schrodinger's cat paradox? If you have to say, is there any kind of particular interpretation of quantum mechanics that your experiments favor, or what kind of interpretation are you more leaning towards in that line?
well, I mean, I think we can do. I don't think I mean, we can do things like Schrodinger's cat, where we can put two different ions, or we can put the same ion in two different places in a superposition state, which sounds a little strange, but that's certainly things we can do. But I would say, so we haven't. I mean, it's been great, and especially nice for the students to do some of these interesting fundamental demonstrations. And so we can make Schrodinger's cats, at least on a small level. But so far there hasn't been any real surprises, even though we can do those kind of things. It's pretty straightforward. But it's still, I mean, it generates a lot of interest for the students to do those kind of experiments.
Yeah. Yes. So thank you. And next question is from Mridul Mishra and also Neelam and Sharang Mishra. So many students actually who are just starting their research, or let's say interest in physics and different subjects. They're asking you a little bit of maybe kind of career advice or regarding your journey. What kind of traits, characters, qualities that that helped you throughout your journey? What helped you to make decisions? Okay, I want to choose this field over that one. Want to proceed with these experiments. So if you could share some light in this regard.
Well, I think just the basic, in my case, just the basic atomic physics is interesting, and it is interesting to do some of these kind of fundamental demonstrations like the Schrodinger cat experiment. And I'd say that it's a particular nice motivation for the students to do things like that. But I think the work is just working with these systems, the kind of precisions and that we can get is I think it's fun to do, and we have these practical applications. We do have better clocks now because of these kind of things, and so I think there's a lot of satisfaction in that. But I think it's just the other thing about it is it's sort of maybe it doesn't have to do directly with physics, but what's nice is we typically are working in a given experiment may be a small team of 2 to 5 people, and just working with other people is I think it's a really nice experiment, and it's people they help each other, I would say, and so it's been just all through my career that's sort of been the mode of operation. That's been really nice for me, and I think other people too. So it's really I would say really rewarding for that reason. So
definitely. Thank you so much for answering that question. Next question is from Ishwita Kumar Das from IIT Roorkee. And the question is, how did you come up with this idea of cooling the ions and trapping the atoms in optical traps? How did this develop for you?
Yeah, well, the cooling, that's make a good example, because so when I was working for Hans Damel, it was on the electron experiments, but I was trying to read outside of the hardcore stuff that related to that experiment, and that was at a time when when dye lasers were first starting to be used, and the nice the amazing thing about dye lasers, they're kind of obsolete now, but the nice thing about the dye lasers, they could be tuned to almost any frequency. And so that really revolutionized atomic physics, I would say, when those came along, because you had these systems that would allow you to work with almost any atomic species. And so that was a big impetus to the field. And anyway, so that was certainly one interesting spin-off that that happened. And I would say there's maybe even with ions, there's I mean, now there's commercial interest, but there's on the order of 100 groups actually doing some aspects of just trapped ions around the world. And so it's a big area, and I think there's a lot of congeniality, I would say, when we go to meetings. It's nice to see what other people are talking about, think about. So it's really it's a lively field right now, I would say.
Yes. On the similar line, I mean, it's a bit more a question where Balaram Sahu from Indian Institute of Sciences, Bangalore, is asking about the experiment that you just talked about. He's asking, can you clarify a little bit about, how you generate these single ions and electrons, and how are you sure that they are single electrons or single ions that you're looking at?
Yeah. Well, I think, I think one way, say that taking the single electron, the single electrons, I think that I showed you the staircase picture, and that's pretty direct evidence of how many ion, or in that case, how many electrons we had in the trap. And the other thing with the ions, that in the traps, that the Coulomb repulsion holds them apart, so they hold individual places in that geometry. So, but we can focus laser beams on to see. Well, we can either illuminate single ions, but we also make pictures, and so we can literally make pictures and tell how many ions we have, for example. So that's become fairly straightforward, that part anyway.
Yes, definitely. Thank you. So there's I'll take a little bit technical question from your presentation. So Rishabh Pal from IIT Tirupati, he asks, as a part of your research, you want to develop a frequency standard based on calcium ion. But according to the figure you showed, you're not driving the so-called S to D clock transitions. Is there any other transition you are taking, or there is any other reason for that?
Well, the one I showed you in mercury, that's a intercombination line, sort of singlet S0 to triplet P0 transition. So it's the radiation is highly suppressed. So that, in fact, the aluminum, maybe I had it written on the slide, but it has an upper state lifetime of 20 seconds. And so the Q is, the intrinsic Q is extremely high. And so that's certainly of interest for the clocks too. So, there are, we can realize some pretty extreme situations, I would say.
True. Yes. Thank you again. So Dipendu from IIT Guwahati is asking, first he's saying thank you for your very inspirational talk. And he asks if you can give a brief description on how different topological phases of matter can be linked to quantum computation.
Oh, but sure that person knows more than I do about
I think he's talking about some, superconductors,
Yeah,
like topological quantum computing.
Yeah, I must admit I don't know about too much about topological quantum computing, but
Definitely.
yeah, he could tell me, or he or she, whoever asked the question, could tell me more. I'm sure better than I could tell them.
Mithilesh Parith from Hong Kong University of Science and Technology is asking, I'm pursuing PhD on ultra cold atoms. So this would be maybe related to your field. He says, what are the problems that will be interesting for him to explore in future? It's a bit of general question.
Oh, I mean, I think well, for example, one thing we've started to think about, people are, people are interested in dark matter, and one of the things, people speculate about is dark matter I mean, the way it's usually described, it may, cause shifts in the fundamental constants. So you want to look for time varying signals that you can't explain otherwise. So I mean, that's one thing that we, certainly a lot of people are thinking about. And there's ways that it might show up in atomic ion spectroscopy or atoms in general. And so that's certainly one thing we're collaborating with some people trying to, work on those ideas. But it's a bit of a shot in the dark kind of that, whether we'll see anything, because but still, even if we don't see anything, you put limits on various effects that people postulate. So anyway, that's one of the interesting things.
Yes. Yes. And on the similar line, Neelam is asking from Netaji Subhash Chandra University of Technology, New Delhi, that it's more like a career-based, again, advice question. What factors should one keep in mind, while deciding his or her research and formulating some hypothesis? What are the factors that you would say, okay, you should think about these and that would for potentially, nice research?
Yeah. Yeah. I mean, certainly, I think one of the things at least keeps me and my friends in is just that there's just a lot of interesting basic problems that we can, and certainly also the technology is really interesting to work with. But I think the one thing, to say is that, if particularly people doing experiments and theory for that matter too. I mean, there's going to be times when when things slow down, you just can't seem to be making progress. And I think so. One thing I always say is, don't want to give up too easy, but you maybe can find something different that you can make more progress on by changing directions. And certainly, that's happened a few times for me in my career that, where you're just finding something you're trying to do is just too hard. But usually you can think of some spin-off that will turn out to maybe even be more interesting. So, it's a balance. You don't want to quickly give up on things just because you're finding it hard. But you have to honestly ask, is this something becoming too hard to work on? So yeah, and of course you want to consult other people too. But certainly, I think everybody goes through that sort of thing, getting stuck at some point. So, as I say, I think I think always having worked with colleagues, I mean, we can help our way out of those kind of problems, So that's never been a big problem, I would say, during my career.
Yeah, thank you. So I see many questions also coming from, now let's say in the subject matter of consciousness and some other fields. So maybe we slowly get into those, and you can share your views and what you think about them. So Jainaran from IIT Tirupati asks, Professor David, we know that the great ideas in many cases are inspired by third-person intelligences, and in many cases, some researchers have attributed it to, some higher power, to God. Have you encountered any such experiences in your discovery or in your journey?
Maybe I'm not sure what you're actually. Maybe you just want to ask me in maybe a slightly different way. I'm not sure what you're talking about here.
So I think, some ideas, like if you see some historical development, some researchers, scientists have attributed them. Okay, I got this idea from, from insights, the intuition, or some attributed to God. So are there such ideas in your life, such discoveries, which you'd like to, share?
Yeah, I wouldn't. Yeah, I don't know. I guess I'm not aligned in that direction. I don't think I don't think there's any really, tough fundamental problems. I mean, I'm not going to be able to ever say why we exist. Those are some things, but there's other more interesting soluble problems. So anyway, I guess so. Those kind of questions, I don't really take too much time to think about, but certainly, just even, in some ways we're, the kind of when we do a precision experiments that there'll be other effects that show up. I think for us, it's usually some physics well explained. In the end, you can explain it physically, but I won't rule anything out there. Like I say, when I ask, why are we here? Why do we exist? That's a tough one. I can't answer.
Definitely. Yes. But thank you for sharing your views. And on the similar line, but I think It's more related to the research from Penrose. If you have come over it. The question is from Devdutt, Himachal Pradesh University. He asks, "What is the material constitute of consciousness? Is it elementary particles known or unknown? And if you can express your views on this quantum microtubules model that Roger Penrose presented, when he's talking about consciousness. So what are your views on this?"
I'm going to have to back out of this because I don't know. I'd have to read what he's talking about. I don't really know. At least I don't
Okay.
recognize what you're talking about there. So,
Okay.
but he's a
So I
smart
think
guy, so it's interesting. Yeah.
yes, definitely. Yes. I mean, there's, I think, some recent research where they show some quantum state collapse of, regarding this microtubules, which they hypothesize to be a constituent of consciousness. Yes. So let's take maybe some other questions. So one of the question is, how do you see the future of the quantum computing? As you also mentioned that there are of course various different platforms and technologies existing presently. So how do you see all the claims we hear about quantum computing, what it can do, and from your personal experience, there's no one better than you to answer this question. What do you
Well,
think about it?
there's certainly a lot of advertising hype with quantum computing, and I think I would say there are real problems that a quantum computer could solve, important problems, and I would say I don't know. I'm optimistic. Even though it's slow. But I'd be just the way science goes in general. I'm optimistic that we'll actually someday have useful quantum computers, and we're maybe not quite there yet, but I think. And maybe we haven't even thought of the right technology, but it's hard for me to believe it won't happen in some larger scale in the future. But that's I don't have any strong evidence to state that, but that's my feeling.
Thank you. So there is one question from, let me see, Avinav Raz, National Institute of Science Education Research. He says, "Is there a fundamental limit to quantum coherence in isolated systems? And what do you think? What are the possible solution to quantum coherence for to increase the coherence?" So he's mostly interested in quantum coherence in isolated systems here.
Yeah, I mean, in atomic physics, you can think about coherence of transitions and things like that, and I think at least I think we have a pretty good handle on what's happening there. So I don't know whether, I mean, maybe there's some things. Maybe I'm not sure what the person is referring to, but I mean, I don't think that, at least in terms of quantum computing, I think that we know what the problems are, or we know that there's hard problems that we having trouble solving. But I mean, eventually, I'm hoping we will find a way, and so that's why I say I'm optimistic. There's, you know, uh, I mean, as I say, there's, one unfortunate part is with, these various quantum computing companies coming, a lot of, lot of, a lot of advertising hype, and so
Yes.
I don't know what to say. Yeah.
Yes, definitely. Thank you for answering that question. So next question is from Aristotle, Spiriton Renaissance International, Singapore. He says, to you personally, what is the value of science for humanity? And what is the goal or meaning and purpose of this scientific advancement and researches? It's kind of a personal opinion of yours.
Well, I don't. I mean, I don't. think I have any novel, answers to that question, but I think just the way, science progresses, I mean, it helps us solve problems and make our life easier and things like that. And so I mean, I think, I think that's the natural way, things go. I mean, obviously also it has, there can be destructive parts about things we learn, obviously weapons of war and things like that. But, I'm, well, at least I'd be overall be optimistic that and feel strongly that I think, the things we learn in science can improve our lives, in some way or other. I think that's, as I say, there's also the other possibility, but in general, I think can be optimistic that in the future, science will help us solve, more problems. So.
Definitely. Thank you. There is a question from Lalit Kishore. He says from PSG College of Arts and Science. The question is, what are the main challenges of observing single ions at low temperatures, and how do they affect the accuracy and scalability of an experiment?
Yeah, well, that's a real problem, but I think with that's for example with the clock problem that's we're trying to solve and see what the limits are. But I think I think you know I think there's a lot of room for improvement, and we have to. I would say I don't know whether there's, for example, when I think of clocks, I don't know there's going to be any fundamentally new problems we're going to have. Although, there's these issues, maybe we can detect dark matter and things like that, but that would be great. But I don't know whether, I mean, I just see this general progression. I don't see why it's going to stop, and just the one case of clocks, they continually get better, and they have over the centuries, so I I don't think we're gonna hit a brick wall on anything.
Yes, thank you. So the next question is from Himansu from Indian Institute of Technology, Tirupati. He says, what are the things to consider when choosing the ion candidate? He says that few groups have taken aluminium, calcium, ytterbium, strontium. So can we take any atom or ion, or what's the basis for this?
Well, I think a lot of times it's just what the technology will allow. So I mean, uh, we may not. I think the basic ideas are sound, and we can think about even higher performance clocks, for example, and but we just don't have maybe don't have the means, the equipment to do the investigations we want to do. But anyway, I don't know. I think that the progress will continue, but there's no magic, to say here about it. We just things are improvable. The technical improvements are always happening. So yeah.
Yes, definitely. Thank you. Nikhil from ISA Kolkata asks again a question, which is, what are the habits a researcher should cultivate, to pursue excellence in science and contribute towards the growth of science? It's more like a question from a student who is, want to continue science as a researcher.
Well, I think the problems that we face are really interesting, and just even something as simple as, say, improving the precision of a clock. I mean, I think that's an interesting challenge. And it's never going to go away. So I think that anyway. I think that it'll keep me going. But I think that one thing to say is I think all of us, in our careers, there's going to be times when we, hit a problem that we just can't seem to, get around. And I don't think, you don't want to give up too early. I guess I maybe was saying this already. You don't want to give up too early, but I think, you can always make a turn and find something even more interesting. And that's certainly, I feel like I've been in that position a number of times through my career. And the other thing too, I would say this doesn't have to do, it's not technical, but I think you need, um, uh, you need some way to get away from, you're going to be in lab working long hours and at times, and you need something to get away. And it could be reading a book, or I don't know, going on a hike or something like. For me, it was bicycle riding. I could just get lost going up mountains and things. But all I'm saying is, I think you can't, you have to, especially when you're having difficulty making progress, you need to, just shift gears, do something a little bit different for a while, and I think it'll come back to you. I mean, that's happened a number of times to myself, so, but I don't think you can get discouraged. Everybody goes, through those kind of things. So.
Yeah, I mean, thank you. That would be my next question. That what are your hobbies and what do you do other than research? But you already answered that. You love biking and all those things. What do you think? What is the importance of? Yes, yes, please. Do you have
Sorry.
any other?
Go ahead.
No, I just wanted to ask you about your hobbies and things that you do beyond outside the lab and this. But you, I think, answered and told that you love biking around. Also, I wanted to ask how important is the collaboration, in these, how important it is to collaborate with other people, other researcher to progress in someone's personal research life.
I mean, I think it's always a good thing, and I think people, you don't. I mean, you see some groups where maybe people are taking too much credit for what's going on, but I think that, especially in my role as group leader, I mean, I can intervene and, not let that stuff happen, So there's always going to be, maybe some rough times, or maybe you don't get along with someone or something like that. But I think, you have to, you have to be reasonable about approaching it. It happens, I think it happens to all of us, but I think you just have to be open with the people you're working with, and usually you can get around problems like that, I think. But
Yes.
I don't have any great wisdom there.
So I mean, I see many questions which are similar to what we have already discussed. So maybe I'll just skip them. Mostly about how one should conduct research and everything. Maybe I take one question in similar line. Shravan Kumar, he's asking how to maintain this continuous enthusiasm. When someone is especially when they're doing fundamental research, because this needs a lot of patience, and we don't. So at this situation, how to keep this enthusiasm?
Yeah, I mean, I don't know. I was trying to, getting to this a little bit, but I think, I mean, there's always the challenges which are interesting to overcome, and that's a big motivation. But as I say, I think that, you do have to examine yourself to say whether you're, you know, continuing on the right path, especially if you hit some major roadblock that's slowing you down. I think you do have to shift and do something else. But I think that's, I don't know, I just think that's part of the process that you know, I mean, there's enough successes along the way. I think certainly what kept me going, maybe they're little tiny successes, but that's what's makes it worthwhile, I think. And I do want to say that, I mean, I wouldn't be able to do this stuff if I was working solely by myself. I think that the interactions with other people is really important. And certainly my best friends in my life have come with people that I worked with in science. So, I think that's an important part.
Yes, thank you so much. Hanshika Tiwari from Hardcore Butler Technical University, Kanpur, is asking, who is or are your inspirational physicists? Someone who has inspired you as a child, as a researcher, to in physics or science.
Yeah, I don't know. I mean, I guess certainly my father was that. I felt that way about my father. But I don't. I mean, and as I said, a lot of people I've worked with, they're nice people in addition to being able to do good work with. But I think so. I mean, I feel lucky in that way. Just that certainly most of the people I've worked with, just turned out to be really good friends. And there's a few that I don't keep friends with, but it's not a big deal. So yeah, I would say, I mean, I don't know. I've never lost interest in this stuff. So anyway, but
yeah, thank you for answering that. There is a question from Pinaki Singha, Indian Institute of Science Education Research, Bhopal. The question is, how does the development of non-Hermitian physics and PT symmetric models contribute to the advancement of quantum experiments?
yeah, I have sort of mixed feelings there. That I think, I mean, a little bit, yeah. Like, I mean, I know the kind of thing, the sort of non-Hermitian physics, that. I mean, there's even some experiments that we've touched on doing that, but and I don't know. I think it's not going to change physics. I think, So I guess one thing I would have said, there has been, even with, in the case of atoms and ions, people have come up with these non-Hermitian things, but I don't know. Maybe. Well, I haven't seen anything super useful come out of it, practical advantage. But I think it's interesting, to investigate these things. But I don't know. Maybe I'm being too harsh, but sometimes I think it's parlor tricks that we're not really learning anything new. I mean, we haven't changed physics with these non-Hermitian experiments. And what would be great I mean, I'm not saying it shouldn't be looked after, but it's not clear. It's not clear that if it doesn't really help us, I don't know whether it's hard for me to get too interested in it. But anyway,
Yes.
that's just personal.
Yeah, thank you so much. So maybe I'll take a couple of questions, then we will conclude it for today. So there's a question from Fabian Rashid, Indian Institute of Technology, Hyderabad. So he's asking, could reality be understood as a shared frozen state maintained by the collective consciousness of numerous observers? So in a way that is analogous to the quantum zero effect, where continuous measurement prevents a quantum state from evolving.
What was the first part of the question?
So the question is about, can the reality be understood as a shared frozen state, which is maintained as a collective consciousness of numerous observers? And he gives that, okay, in the same way as the quantum zero effect, where continuous measurement prevents. Yeah.
I don't, yeah, I'd say I don't think so, but maybe I'm not. I mean, I maybe have a pretty simple picture of the quantum zero effect. I mean, we had experiments in the quantum zero effect, but it's more, just for entertainment purposes. I don't think we were learning anything new about physics doing those kind of, I mean, it was interesting to do them, but I don't know. So maybe I'm not the right person to ask that question to.
Thank you so much. Maybe the last question. I mean, we have many questions coming, from the participants, but I see that most of them are similar to what we have discussed already. Some of them are maybe a little bit, different topics. So to conclude at least this session for today, what is your message to our young researcher audience who are present today here in this congregation, in this conference, listening to you? What is your message to them regarding science and research?
Well, I think I guess my view is pretty simple. You want to find something you're interested in, and and also there's this issue. You may get. I think we've touched on it before here that you can maybe run into roadblocks that really are just too difficult to overcome. But my feeling has been just, I mean, you have to be aware of that when you're running in your head into the wall. But I think I think you just have to be able to stand back and just figure that either maybe change direction, because I think you'll always, changing direction, maybe you'll find something even more interesting or more, fulfilling than what you've been working on. But I think that's sort of normal for all of us. You're going to find roadblocks at sometimes, and just maybe taking a turn or whatever, helps. And I mean, I certainly count too many cases of that in my own career. So.
Yes, thank you so much, Professor Wineland, for beautifully answering all these questions that I have been bombarding to you from all our participants. So we'll just have a few more things left for the session, for the event today. I would like to invite Dr. Dheeraj Dubey to convey a vote of thanks. Dheeraj Dubey, please.
A very warm greetings to everyone. It is truly an honor to deliver the vote of thanks for this remarkable occasion. To begin with, I would like to extend my heartfelt gratitude to the visionary who has redefined the fields of quantum mechanics and atomic physics, our distinguished speaker, Professor David J. Wineland, who is a Nobel laureate in physics. Despite his demanding commitments, he generously accepted our invitation and joined us virtually, enriching us with his profound insights on his journey of discovery. Let us all extend a heartfelt round of applause to Professor Wineland. Professor Wineland, your lecture was nothing short of an extraordinary. It provided profound insights into the connections between science and the vast mysteries of the universe. Your groundbreaking contributions to quantum mechanics, particularly your pioneering work with individual quantum systems, have revolutionized precision measurements and opened new doors in quantum information technology. Through your insights, we have come to appreciate how quantum systems' precision and harmony reflect the deeper truths of nature. Personally, I have found your talk inspiring as it demonstrated how the quest for accuracy and the exploration of the unknown resonate deeply with faith, a fundamental element of life. Scientific inquiry, as you beautifully articulated, emphasizes our interconnectedness and the guiding forces of existence. Once again, let us give a warm round of applause to Professor David J. Wineland. Now, in today's fast evolving world of technology, it is truly inspiring to witness individuals and institutions dedicated to fostering meaningful dialogue and the pursuit of knowledge. I'm deeply appreciative of the collective effort from all the organizations that contributed to ensuring this lecture reached a diverse and engaged audience. I'm particularly grateful to our knowledge partners, IIT Hyderabad, the School of Humanities, Social Sciences, Management, IIT Bhubaneswar, IIT Tirupati, Dr. T.T. Singh's Quest Club, IIC Bangalore, Jigyasa, Science Consciousness and Inner Quest Group, IIT Bhubaneswar, SOA University, Bhubaneswar, MT University, Gurugram, Sister Nivedita University, Kolkata, Sanskrit University, Mathura, and Government PG College, Rani Khet. Their unwavering support ensured we reached a wide and diverse group of students and professionals. I would also like to thank CSR Labs, AIMS Guwahati, IIT Guwahati, IIT Dharwad, IIT Roorkee, NISER Bhubaneswar, Manit Bhopal, NIT Nagaland, NIT Agartala, NIT Puducherry, and many other academic institutions for promoting this lecture within their campuses and encouraging active participations from students and professionals alike. On behalf of the Bhaktivedanta Institute, I sincerely thank the management of these institutions for their invaluable cooperation. The success of any event lies in the energy and engagement of its participants, and today it has been no exception. I sincerely thank every attendee for their active involvement, thought-provoking questions, and unwavering attention throughout the session. Your contributions have truly elevated this event into a memorable and impactful experience. Behind every successful event lies immense effort and meticulous coordination. I would like to extend my acknowledgement to the incredible contributions of our student volunteers who work tirelessly behind the scenes, from designing posters to ensuring a seamless execution of the program. Their dedication has been key to the event's success, and I extend my heartfelt thanks to each one of them. Lastly, I express my deep appreciation to Srila A.C. Bhaktivedanta Swami, the visionary founder Acharya of the Bhaktivedanta Institute, and Dr. T.D. Singh, the founder director, whose groundbreaking efforts in fostering a science-spirituality dialogue have brought all of us together today. I'm also grateful to the Almighty for providing this platform and guiding us towards organizing more impactful events like this. As the Bhaktivedanta Institute celebrates 50 years of dedicated service, I would like to thank all its members, past and present, who have contributed to initiatives such as the World Science Congress, AISSQ, Summer and Winter Schools, publications, BHIMA, essay competitions, seminars, symposiums, and lectures. To conclude, I thank everyone who had made this lecture an enriching experience. I look forward to seeing you at future events. Thank you once again, and have a great day.
Thank you.
Yeah, thank you.
Thank you, Dheeraj, Dr. Dheeraj Dubey. Yes, so Professor Wineland, I would just like to tell our audience about this upcoming conference. So we have this conference coming up, which is, I hope you can see my screen, is the Science and Spiritual Quest. As the end of the year in Vijayawada, India. We have Professor Reinhard Genzel, as it was also mentioned in the beginning, and the student and the participants can bring their poster along and interact with everyone there. So it's a nice opportunity. Please, everyone can contact the number provided, and for the details, go to the website. And also, as mentioned earlier, we have this new release, Students Magazine, which is available at the store.binstitute.org. So whoever wants to have a copy can reach the website and get one for themselves with very interesting articles. So at the end, I would like to
once again thank Professor Wineland from all of us, from everyone present here, to take your time out and making it to this talk and sharing your wonderful journey with us. Thank you all, and we hope to have you in our future events. And yes, thank you, everyone.
Well, thank you. You know, I've enjoyed doing it, so thank you.
So I think with this, we would like to conclude today's event here. And I wish you, all of you, have a nice rest of your day.
All right. Thank you. You too.
Thanks.
All right. Bye-bye.